today we are going to discuss about the relative motion of one particle with respect to the other particle that can be described. Now, if you have two cars which are moving at same velocity, even though they are moving with respect to an observer on the road, they are not moving with respect to each other. A passenger in one car will see the other car at the same distance. Thus, with respect to time, the other car is not having any velocity with respect to passenger in the car. We say that the relative motion of one car with respect to the other car is 0. We will discuss this problem in a more general way when the cars may not be moving only in the straight line, but they may be undergoing curvilinear motion. Now, this is one animation showing the motion of two cars, red car and blue car. Now, the driver in the red car always sees blue car with it. So, therefore, with respect to the red car, blue car is not having any relative motion. However, drivers will come to know that they are moving at a high speed because they will see the other surrounding objects like tree and all this. Outside person is seeing that both the cars are moving with the same velocity. We are familiar with the concept of relative motion. In train also, sometimes we get illusion that the train is moving because the other adjacent car starts moving. But when we see other objects like poles etc., then we get the idea that it is our train is really not moving. Now, in a way, we attach one axis system in our mind. When we observe the objects moving, we have some reference frame. In that reference frame, we study its motion. So, therefore, this lecture can be considered about expressing the displacement, velocity and acceleration with respect to particular coordinate system. Now, that coordinate system itself may be translating with respect to another coordinate system, or it may be rotating. Imagine that a boy is revolving a rod in a horizontal plane in the circular path. Now, if a particle is situated at the middle of the rod and another particle is at the end of the rod, then the particle which is at the middle of the rod will always see the particle at the end of the rod. Therefore, what happens that it may observe that the particle is not having any relative motion with respect to this. However, from outside we observe that both the particles are having different velocities. Particle which is at the end of the rod moves with a higher velocity compared to the particle which is at the middle, and therefore, there is a relative motion between two particles. However, since we have taken a rotating coordinate system, that is why the middle particle does not observe the velocity of the particle at the end. Now, therefore, it all depends on what type of axis system we have chosen. Now, here in this figure O, x and y are the axis system shown, and this is the one particular particle point is indicated by B. RB is the position vector. This is A, another point is A, RA is the position vector. If we fix a coordinate system, you can consider that B may be one particle, A may be the other particle. Both may have different velocities, but if we fix up another coordinate system attached to the particle B, which is indicated by x and y, in the most general form it can have this thing. Now, we are interested, supposing an axis system is moving with respect to the other axis system, that means small x y is moving with respect to another axis system, that is Ox and Oy system, x capital Y system, then what is the relationship between velocities in two systems? Now, the difference between these two position vectors RA and RB is indicated by another vector, that is called BA. RB plus BA gives you RA. We can write R is equal to RA with respect to B. So, this is the position vector of A with respect to B, which is indicated by R. Now, once we have already mentioned that x y is a fixed reference frame and small x y is a moving reference frame. To begin with, we consider that x y axis only translate with respect to x y, but they do not rotate. Like in the previous examples, one car is translating with respect to the other car, but it is not rotating because they are moving in a straight line path. Now, this case becomes quite simple. If A is any particle, the position vector of A as measured relative to the frame x y is RAB is equal to xi plus yj, where subscript A/B means A relative to B or A with respect to B. X, y are the components of the position vector, and they have been expressed here in terms of the unit vectors in the frame x, y. You may have adopted unit vectors in the fixed reference frame. That means, we could have said that capital I hat and capital J hat. However, it is known that if the axes are parallel to each other, if small x is parallel to small x, small y is parallel to small y, in that case capital I hat will be equal to small I hat. In this case, we have expressed it x I hat plus y j hat. Now, the position vector of A with respect to x y is given by R A is equal to R B plus R A with respect to B, that is R A slash B. Now, with this we can differentiate this position vector with respect to time, because we know now we have some idea about vector calculus. Vectors can be differentiated. Now, differentiating it with respect to time and indicating the differentiation with respect to time by dot, we get R dot A equal to R dot B plus R dot A slash B. R dot A is nothing but the velocity of A, change in the position vector of A, because R A is the position vector with respect to OXY frame, capital X capital Y frame. Therefore, R dot A gives the absolute velocity of point A, that is indicated by V A. Similarly, RB is the position vector of B in capital X, capital Y reference frame. Therefore, R dot B indicates the velocity of point B, that is absolute velocity B, plus V A with respect to B, because R A B is the position vector of A with respect to B. Therefore, R dot A B will be velocity of A with respect to B. So, therefore, we get a simple relation that V A is equal to V B plus V A slash B. That means, velocity of particle A is equal to velocity of particle B plus velocity of particle A with respect to B. This, therefore, absolute velocity of a particle is the vector sum of the velocity of a particle with respect to a translating frame of reference and the velocity of the frame itself. If we say velocity of the frame, because frame is attached at B, therefore, V B can be called as the velocity of the frame, and V A B can be called velocity of the particle A with respect to this translating frame which is attached at particle B. Okay. So, we need not mention again about that there is a particle B. Instead, we mention that there is a particle A whose velocity is measured with respect to a reference frame which is moving. Reference frame origin is indicated by B. B may be physical particle or may not be particle. Now, in the same way, we can find out accelerations. We take the double derivative which we indicate by double dot on the vectors. So, R double dot A is equal to R double dot B plus R double dot A B, or A is equal to A B plus A with capital A slash B. Here in this case, AA is the absolute velocity, absolute acceleration of point A, AB is the absolute acceleration of point B, and A slash B is the acceleration of point A with respect to point B in the reference frame which is moving. Now, thus the absolute acceleration of a particle is the sum of the acceleration of the particle with respect to the translating frame and the accelerating of the frame itself, because we can say that AB is the acceleration of the frame, that means AB is the acceleration of the origin of the moving reference frame. Also, we in the component form we know R dot AB, which is the velocity of A with respect to moving reference frame, that can be written as x dot I plus y dot j. Note that I and j have 0 derivatives with respect to time, as these are now constant vectors. In translatory motion, the I and j does not change with time. Their direction and magnitude both remain constant with respect to time. A translating reference frame which has no acceleration is known as inertial frame. If a translating reference frame is having an acceleration, it is known as non-inertial frame. A rotating reference frame cannot be an inertial frame. A inertial frame is that reference frame which is translating with respect to the other reference frame with constant velocity. Now, we present one example of using these relations. In this figure, capital X, capital Y system is shown, that is fixed reference frame. Now, in this frame, a cardboard is moving in this plane floor with a velocity phi phi plus 5j with respect to fixed xy axis. Now, in this cardboard, which is black cardboard, on this a particle is rotating in a blue circle of radius 2 units with a angular speed of 5 radian per second. Question is, what is the absolute, that means with respect to xy frame, velocity of particle when the particle is at point P? This is the velocity of the particle P has been shown here. There is a, we can attach an axis system xy which is translating with respect to capital XY. This moving axis system has been indicated by red lines. Now, fixing the xy axis system at the center of circle, with respect to xy system, velocity of point P is given by omega class r, that means omega is mentioned that it is r is 2 unit and omega is 5 radian per second. So, this is 2 into 5j, that means it comes out to be 10j unit. 10j. Here we have to notice that this small j is the unit vector in the moving reference frame. Now, this is small j is in the moving reference frame. I could have said capital J also. Of course, in this particular case, capital J will be same as small j. So, one has to always pay attention that in which system he is expressing the unit vector. So, with respect to xy system, velocity of point P has been specified as 10j. Thus, the absolute velocity of P is equal to the velocity of the reference frame itself plus the velocity of the particle in that reference frame. It has been already mentioned that the cardboard is moving in a plane floor with a velocity phi phi plus 5j. That means the reference frame which is attached with the cardboard is having the velocity phi phi plus 5j. Therefore, absolute velocity of P is phi phi plus 5j plus 10j, that is equal to phi phi plus 15j. One has to notice that although I am talking about the absolute velocity of particle P, however, the answer has been expressed in terms of the unit vector in the moving reference frame. This is all right. One can, if one wishes, one can write final answer in this manner also, which is also equally correct, 5i plus 15j, where now I and j may indicate the unit vectors in the absolute reference frame. It is, however, this is not so important to always express the absolute velocity in the absolute coordinate system. Any coordinate system can be adopted. Only thing that one has to understand that what are the, in which coordinate system the components have been expressed. Now, we discuss about the acceleration of the particle. With respect to xy system, that means with respect to moving coordinate system, acceleration of the particle is equal to minus omega square r. I have used minus term, it is directed at the moment, it is directed towards the negative x direction. Therefore, this is equal to minus 25 into 2, omega is equal to 5 radian per second, r is equal to 2 units. So, this becomes minus 50 units towards center. The acceleration of x y, that means 50 units towards center, that is why minus 50 sign. The acceleration of x y with respect to capital X y system is 0 because the cardboard is moving with a constant velocity. Hence, the absolute acceleration is minus 5I itself. Now, we discuss the rotating axis system. Let us consider axis system xy which rotates with respect to capital X y, capital X capital Y system. Again the same figure, that here also the same relation is valid, that RA is equal to RB plus RAB. That relation remains same whether this coordinate system is moving, translating or rotating. Now, we also define that the angular velocity of the rotating axis is omega, where omega is equal to theta dot, that means d theta d dt. You have the axis x, small y, it rotates by an amount theta because it is rotating. So, this theta can be differentiated with respect to time. Now, we can easily see that if the unit vectors I and j are expressed in the moving coordinate system, that means rotating coordinate system, then di by dt will be omega times j and dj by dt is equal to minus omega times a. In the translating reference frame, di by dt was 0. However, in the rotating reference frame, di by dt will not be 0 because the vector is, although it is maintaining the same magnitude, but it is rotating, that means it is changing the direction. This is apparent from this figure. Here the unit vector I has rotated by an amount d theta. Therefore, there is a change in the position of the vector. So, if this is the vector after d theta time, this is vector before, their difference is indicated by another vector, and its magnitude will be equal to d theta because these are this one, and it will be in the j direction because in the limit d theta tends to 0, that di approaches the j direction, and therefore, if we differentiate di with time, we get d theta by dt, that is omega times j. Similarly, the vector j has rotated to a new position, therefore, dj will be directed towards this side, this is dj, that is, and its magnitude is naturally, it is a unit vector. So, it is d theta only. So, dj, but it is in the minus direction of I because positive I is this direction. So, therefore, it is minus d theta into j. So, dj is equal to minus d theta into I. If angular velocity is denoted by the vector, that is omega is equal to omega, that is d theta by dt or theta dot multiplied by k hat. K hat is the unit vector along the z direction, that is normal to the plane. Then we can also write that it is basically omega di by dt is basically omega cross I. Like that, dj by dt is also omega cross j. Now relative velocity of the point A with respect to moving frame xy can be found by differentiating the basic relation. Ra is equal to Rb plus Rb slash A. Differentiate it with respect to time, we get R dot A is equal to R dot B plus d by dt xi plus yj is equal to R dot B. Now differentiating xi with respect to time, we get one term x into I dot plus x dot into I. Then we get y times j dot plus y dot j. In this case, I dot is not equal to 0. Instead, I dot is given by omega cross I. So therefore, we get R dot P plus omega cross xi plus omega cross y j plus x dot I plus y dot j. Omega can be taken common and it will become omega bracket xi plus yj, which gives you Vb plus omega cross r plus x dot I plus y dot j can be called as V relative, because this is the velocity of the point A in the frame of reference, moving reference frame. So that is the relative velocity here, because position vector is xy. So therefore this is the V relative. Thus we get a nice relation, that is Va is equal to Vb plus omega cross r plus V rel. So we get one extra component Vc, that in this case V rel is in fact not equal to Va minus Vb. Instead, we get one additional term which is important, that is omega cross r. If the reference frame is only translating, in that case omega becomes 0. For a translating reference frame, omega is 0. Therefore, Va is equal to Vb plus V rel. Likewise, we can find out the expressions for the relative acceleration. The relative acceleration equation may be obtained by differentiating the relative velocity relation. Relative velocity relation is given here, that is Va is equal to Vb plus omega cross r plus V rel. Differentiate Va with respect to time, you get A. Differentiate Vb with respect to time, you get AB. Differentiate omega r with respect to time, you get two terms, because it is a cross product of two vectors. One is given by omega dot into cross product r plus omega cross product r dot. Differentiate V rel with respect to time, you get V rel, that is differentiation of V rel with respect to time. Now it is known that R dot, in this previous expression we got a term R dot. Let us see what is R dot. R dot is d by dt xi plus yj, which can be written as xi plus yj, xi dot plus yj dot plus x dot I plus y dot j. X, which can be written as omega cross r plus V rel. This relation we have derived. Therefore, omega cross r dot can be written as omega cross bracket omega cross r plus V rel. which is equal to omega class bracket omega class r bracket close plus omega class v rel. Now, v dot rel is basically d by dt x dot I plus y dot j, which can be written as x dot I dot plus x plus y dot j dot plus x double dot I dot plus y double dot j dot, which is equal to omega class x dot I hat plus y dot j hat plus x dot I hat plus y dot plus x double dot I hat plus y double dot j hat, which can be written as omega class v rel plus a rel. So, here again we observe that v dot rel is really not equal to a rel. Relative velocity, if you differentiate with respect to time, you do not get a relative acceleration, you get one additional term as well, which is omega class v rel. In the translating reference frame, omega I becomes 0, therefore v dot rel is equal to a rel. That means, in the translating reference frame, if you differentiate the relative velocity, you get the relative acceleration, but the same thing is not true for the rotating reference frame. Thus, AA is equal to, we get this big expression AB plus omega dot R plus omega class R plus 2 omega class V rel plus A rel. Let us identify each term in it. Omega class R is the tangential acceleration, since it is perpendicular to unit vector k and r. Omega is having the direction k, therefore, omega dot is also having the direction k. Omega class is the vector which is in the tangential direction. This is shown here. Omega class omega r is normal acceleration, since it is directed towards b. Omega class r will be towards j, and j class k again gives you I. So, this is in the towards b, and this is called normal acceleration, or the same thing as the you get centripetal acceleration. Now, 2 omega class v rel is the other term which we get in the expression for acceleration. 2 omega class v rel is really the Coriolis acceleration. This is named after the French military engineer G. Coriolis, who was born in 1792 and died on 1843, who was the first person to call attention to this term. This acceleration is normal to k and v rel. So, if the particle is moving, if the path of the particle is like this, and you have the relative velocity of the particle like this, rotate the relative velocity vector in the direction of rotation, give 90-degree turn, you get the direction of Coriolis acceleration. That means, if this is the relative velocity, suppose there is a link on which this slider is moving, and link has velocity like this, that means it is moving in the counterclockwise direction. Relative velocity of the slider is shown like this. You have to, because it is rotating in the counterclockwise direction, link itself is rotating in counterclockwise direction, therefore, rotate the relative velocity in the counterclockwise direction. This is the direction of the Coriolis acceleration. Similarly, if the rod link would have been rotating in the opposite direction like this, then the Coriolis acceleration would have been like this. So, Coriolis acceleration can be in both direction. Normal acceleration course is directed towards the center of the curvature. Now, having told this, we will solve one example of relative velocity with respect to rotating frame. Now, let us consider this problem. In this figure, there are two cars. Blue car is moving on a circular path whose radius is of the curvature is 200. The red car A is moving in a straight line and it is approaching towards B. So, car B is rounding the curve with constant speed of 15 meters per second and car A is approaching car B in the intersection with a constant speed of 20 meters per second. The distance separating the cars is 40 meters at the instant depicted. That means this distance is, you can say, 40 meter. Size of the car is very small compared to the distance 40 meter. So, it can be treated as a particle. At the instant depicted, VA is equal to 20I, because it is mentioned that car A is approaching car B with a constant speed of 20 meter per second. Therefore, VA comes out to be 20I. VB is moving with 15 meter per second on a circular path. At the instant depicted, VB will be equal to 15J. Now, apply the relative velocity formula. VA is equal to VB plus omega cross R plus VL. We are attaching the reference frame, moving reference frame in car B. So, therefore, this is x, unit vector is in the I direction, that is I, then yj. This reference frame is rotating on a circular path. Now, therefore, velocity of A is given by velocity of B, which is the velocity of the origin of the reference frame, that is same as the velocity of the car, plus omega cross R plus VL, which is the velocity as seen in the moving reference frame or as seen by the driver in car B, because the driver in car B is moving with respect to that reference frame in the same. Putting the values, VA is equal to 20I is equal to 15J plus 15 by 200, 15 by 200 is the omega cross minus 40J, because minus 40 is the R plus VL. Therefore, solving this, we get VL is equal to 20I minus 12J. This is the velocity of the car A as observed by the person sitting in car B. Remember, car B was having the velocity of 15J and car A was having the velocity 20A, but the relative velocity did not come 20I minus 15J. Instead, it is coming 20I minus 12J. Had this car been moving in a straight line, then omega would have been 0 and the velocity would, relative velocity would have come, instead of 20I minus 12J, it would have come 20I minus 15J. So, therefore, see the difference a rotating coordinate system makes. this is the velocity mentioned there is the velocity of car A as seen by the driver, who is treated as a particle along with the car in car B. Will the driver in car A will see the velocity of car as VL is equal to minus 20I plus 12J. If the velocity of car A with respect to car B is 20I minus 12J, can we say the velocity of car B with respect to velocity of car A is minus 20I plus 12J? No, we can't say this. Let us see this thing. Suppose the axis system is attached to A. Then VA is equal to VB plus VL. In this case, the axis system is attached to this one. This axis system is not rotating. So, there is no omega, omega is 0. Therefore, the expression comes out to be VA is equal to VB plus VL, or VL is equal to 15J minus 20I. Thus, we see that the observations of both drivers are not the negative of each other. That is this thing. So, therefore, it is very important to understand the relations in the translating as well as rolling reference frame. Now, let us discuss some problems on the concepts developed. Now, imagine that a particle is moving, a particle is located at B, that is periphery of this one, and the disk is rotating with an angular speed omega. Now, if we attach a moving reference frame at B, this is x radial direction, other is this one, then this frame of reference also rotates with velocity omega. In this case, VB is equal to, we get the relation, if we fix the coordinate system at A. So, VA is equal to VB plus omega cross minus omega cross R plus VL. If the A is a fixed point, then VA is equal to 0. So, therefore, 0. Now, in this case, I have fixed an axis system here at omega cross R at this point. Therefore, I have to take this R as minus R. This is minus. So, therefore, this is VB, and I can write VB as omega cross R, where R is the radius of the circle. So, this becomes omega cross R. This is minus omega cross R plus VL, which gives us VL equal to 0. That means, if a particle is placed at B and an axis system is attached with that particle, the particle will observe that center is at the same position, and therefore, you are getting VL is equal to 0. However, if we fix up an non-moving coordinate system here at particle A, then velocity of particle B V are related with velocity of A in this fashion: VA is equal to VB plus V L. As the axis system is not rotating, therefore, I am not putting omega. Now, here VA is equal to 0 and this is VA, sorry, this is VB, VA plus VL. So, therefore, VB is equal to VA plus VL. Now, VB is known as omega R, and VA is equal to, that is tangential direction, this velocity is omega cross R, we can write in the vector form omega cross R is equal to VA, that is 0 plus VL. So, therefore, the relative velocity comes out to be omega cross R. That means, if you attach an axis system at point A, then it will observe particle B to have relative velocity omega cross R. However, what happens if the axis system, although it is attached with A, although it is at A, but unlike in the previous case, it is not fixed, it is also moving with the disk. In that case, we have an axis system which is having the velocity omega. Now, consider a particle B here. The velocity B is equal to VA plus omega cross R plus VL. VB in this case is equal to omega cross R, because absolute velocity is known to be omega cross R, which is equal to 0 velocity plus omega cross R plus VL, which gives us VL equal to a 0 vector, indicating that it is not that just particle is not enough, it is important what type of axis system has been chosen. Same particle A may have the origin, one axis system was constant, not non-moving. In that case, VL came out to be omega cross R. If the axis system is also rotating with the disk, then VL comes out to be 0, which is inconsistent with our intuitive reasoning. As the axis system is rotating, it always follows particle B and thus is not able to know the difference in the position. Now, this now we will discuss one problem concerning this principle. Here this is link ring is there, and this ring is having a slot, and this slot is a bar is kept, which can spin is kept, which can slide, and this is another ring which is hinged here. Now you may be asked to solve this problem, that given that you have the angular velocity omega and this point is point A, this point is point B, this is the point, then this is point B. You have to find out the velocity of point B with respect to point A, and also the angular rotation of this ring, that which can be called as BC. So, such type of problems also can be solved using the previous equation. In this case, you can attach one axis system on this rod, and then which is rotating, and then you can have VB is equal to VA, which is 0, that is omega cross R plus VL. Where at this stage you know the relative velocity direction, that is direction is along this thing, but you do not know the magnitude at this stage. Omega VA is of course 0, omega class R. Omega class R can be easily calculated. You have fixed up the axis system at point A. R is the distance radial, the position vector of B with respect to A. Omega might have been specified to you, so you will be able to calculate omega class R plus, and V will only the direction is known, you do not know the magnitude, but then you know the other equation, that if you have the velocity of point B with respect to point C, that is also this direction has been given. So, absolute velocity of point B is omega class B C, omega class vector C B, velocity C B. So, which also has to be has been given. However, you do not know this is omega, I will indicate it by omega 1, although you do not know that the magnitude of omega 1. Then you have, but you can equate this with this expression omega class R plus V L, and you can find out V L, and you can find out from you can express these in the component forms, and then you can get two equations, and there are two unknowns in this problem. One is the omega 1 and other is the magnitude of V L. So, that type of problem can be solved. Now, we will solve one problem of the simple problem of Coriolis acceleration. If there is a ring here which is rotating at 10 radian per second, and a particle is sliding at 10 meter per second, what is the Coriolis acceleration? Coriolis acceleration will be 2 omega into V. In this case, magnitude will be 2 omega V, that means it will be 2 times 10 times 10, which will be equal to 200 meter per second square. Direction of this Coriolis acceleration will be in this direction. The Coriolis acceleration is not dependent on the position of the slider on the link. It is dependent on the relative velocity. However, there will be another component, that is centripetal acceleration of this particle, which will depend on the relative position, that is given by 10 square divided by r, where r is the distance of this. So, therefore, this component is decreases as the particle moves this one. So, this component is given in this direction. In this problem, the Coriolis acceleration will have the same direction as the tangential acceleration. If the tangential acceleration is provided and it is say 2 radian per second square, then the tangential acceleration will be in this direction and the magnitude will be alpha times r. That means, this is 2 radian per second square multiplied by the distance, this one. So, like that you can solve these number of problems using the equations developed in this things. So, let me quickly summarize what we have developed. We started with translating reference frame and obtained the simple expression that is VA is equal to VB plus VA slash B. AA is equal to AB plus A slash B. However, if the coordinate system is rotating, we get the equations VA is equal to VB plus omega class R plus VL. Remember, there are 3 components here, and we get acceleration components AA is equal to AB plus omega class R plus omega class R plus 2 omega class VL plus AL. So, here we are getting 1, 2, 3, 4, 5 terms. So, these 2 equations are very important. In fact, in this expression, if you put omega is equal to 0, this equation reduces for the equation of the translating reference frame. So, therefore, important equations are, one is this, another equation is, this is in the term of velocity, VA is equal to VB plus omega class R plus VL.